Hey everybody. Still need that theme song. You people are not helping me at all. I don't know. I got nothing. Sorry. I don't want to waste too much of your time. I want to talk about torque and angular acceleration. As some of you probably know about torque, especially gearheads like Dan and Dylan. You guys probably know something about torque. You probably heard it described in foot-pounds. Okay. That's like there's so many foot-pounds of torque. And you notice that torque is how hard you pushed in pounds, the force. But it also has to do with the number of feet, too. And that's actually a measure of the radius. Torque is actually a vector product of an object's radius and the applied force. And we'll talk about why it's a vector product in just a second. I want to point out that it is a vector, which means it's a cross product. So the actual symbol is R cross F. And again, it's a vector. Which means that torque is at a maximum when the radius and the force are perpendicular, and a minimum if parallel. And that sort of makes sense. And I'll explain why. If you're going to apply a force, like say you want to pry open a paint can. Here's my weak paint can. Got like a little lid here. Got your screwdriver in this spot here. Well, let me undo whatever I just did. Oh, sorry. I'll draw it again. And then you put your little screwdriver in there. Well, the screwdriver's about as big as a paint can. If you're going to pry the paint can open, you're going to pull down. And if you look at the motion of it, the motion would look like it was in a circle. This would be the center of the circle. And the distance from here to here would be the radius of that circle. And if you look, you're applying the force perpendicular to the radius. If you took this situation, took the screwdriver, and tried pushing in on the can, you might be able to get the tip further in to the wedged little area between the lid and the can, but you wouldn't be able to open it that way. The best way to open it is to pull down on or to push up. And in both those cases, the radius and the force are perpendicular. In this case, it's parallel. So that kind of makes sense in any combination thereof. So if torque is R cross F, then as we learned earlier, we know that the cross of AB equals AB sine of theta. Same thing is true here, that this is going to be RF sine theta. Yes, sweetie. Where this is the angle between them. So if I have let's say I have this is the pivot point. If this is the radius, and this is the force, then theta is going to be the angle between those. And that makes sense. It also makes sense that torque is the rotational analog of force. Just like moment of inertia is the rotational analog of mass, because it takes into account the radius. And also, in this case, it's force. I do want to point out the units. They are going to be meters times newtons, which appears to be Newton meters. Well, it is, but it's not joules. Joules only work, or they're only joules when force and the displacement are parallel. Otherwise, it's just straight Newton meters. That will actually be something that seems weird later, but we'll talk about it. But those are the units for torque. And if we look at a bunch of examples, let's say we have a I don't know, a teeter-totter or something like that. And we're lifting something up here. And in order to do that, we're going to push down, maybe 10 newtons of force. This is point, we'll make it 7.5 meters. What's the torque put into it? Well, that's actually pretty easy. That's just going to be 10 times 0.75 meters, which is going to be 7.5 Newton meters. Now, again, it's a vector, so we usually state a direction. The direction in this case, if I extended this over and this could keep going, it would go in a counterclockwise direction. Okay. So when we label torque, we usually label it as counterclockwise. There's actually a rule about this, that counterclockwise is positive and clockwise is negative. But usually I don't treat it that way. I just subtract them or add them depending on if they're going in the same direction. But if you think about it, counterclockwise as a positive makes sense because you're going through the quadrants in the same order as increasing radians. So that's why you treat it that way. But it doesn't necessarily matter that much as long as you're careful and recognize the direction you're going. You should be okay. We'll do another example real quick. Let's say that we have a rod here, and we have its pivots here. It's 2 meters long, and we put in a force like this, that of 120 newtons, and it's at 37 degrees. The old 3, 4, 5 triangle angle. Well, the component that we care about is this one, because that's the one that's perpendicular to the radius. So torque is going to be R cross F, which in this case is going to be 2 meters cross 120 newtons. No, that's kind of okay. Times, in this case, the sine of 37 degrees, which would be 3/5. So it's going to be 120 times 3/5. This is going to be, I think, 72 newtons. And we're going to get a torque of 144 Newton meters. In this case, since this is going up, it would make this whole thing turn like this. So it would be a clockwise torque. Or if you want to follow the convention, it's 144 Newton meters. Cool. In the next video, we're going to talk a little bit about how we use Newton's second law with rotation.